In the last lecture of module 6, I will be doing some practice problems on solving second order differential equations. So let us we'll look at a couple of problems, okay, and one of them related to forced oscillations and resonance, okay. But first I'll take a simple problem. So first problem is solve y double prime plus y is equal to 1 by cosine x, okay. So I have a non-homogeneous equation, okay. The right hand side is 1 by cosine x. Now we can solve this by the method of Wronskians, okay, but we need to solve the homogeneous equation. So step 1, solve homogeneous equation. So the homogeneous equation is y double prime, or I will say y h double prime plus y h equal to 0. So this is your homogeneous equation where I just put right hand side equal to 0 and I replace this by y h just to indicate that it is a homogeneous equation, okay. And you can see this is I can write the solution as cos x. So y h is equal to a cos x plus b sin x, okay. So if you take cos x, the second derivative will just give me the function back with a negative sign, okay. So if I add it, I will get 0. Similarly, if you take sin x, you will get the second derivative will again give you the function back. So cos x and sin x are linearly independent solutions. So cos x and sin x are linearly independent solutions, okay. So these are two linearly independent solutions. So the general solution is written as a linear combination of these two. So a and b are arbitrary constants. Okay. So we are supposed to determine a and b, okay, and to determine that you will use the boundary conditions, but this is the solution of the homogeneous equation. Now the solution of the non-homogeneous equation, we will write yp of x, okay, is equal to u cosine of x plus v sine of x, and you know the way to calculate u and v, okay. So you know how to calculate u and v. So u is equal to minus integral. So the second function is sin x, and sin x into the right hand side is 1 by cos x, okay, and this should be divided by w times dx, okay, and v is basically integral of cosine of x into 1 by cosine x dx divided by w. So these are what u and v are, okay, and now let us calculate what w is. So what is w? So if you have sin x and cos x, then w is equal to y1 y2 prime minus y1 prime y2. So this is y1 is cosine of x. So cosine x, y2 prime is derivative of sine, which is cosine x. So you get cos square x, okay, and then now you will have minus sin x into, so you will get minus sin x into minus sin x. So you will get plus sin square x. This is equal to 1. So w equal to 1. So now I can write u is equal to integral of what I had here was sin x divided by cosine of x, sin x divided by cosine of x, and there is a minus sign. So I will take the minus here dx, okay. This is nothing but because derivative of cosine x is minus sin x. So I can write this as logarithm of absolute value of cosine of x. Okay, so this is logarithm of absolute value of cosine of x. Okay, what about v of x? V of x is just now the cosine x will cancel, you just have 1 dx. So v equal to integral 1 dx equal to x. Okay, so I can write my yp is equal to log of cosine x into cosine x plus x sin x. So my general solution y is equal to a cosine of x plus b sine of x plus cosine of x into log of cosine of x plus x sin x. So this is the general solution, and you can see that there are 2 arbitrary constants in this solution, okay, and you can verify that when you substitute this in the non-homogeneous differential equation, it is a solution of this differential equation. Okay, so this is an illustration of the method of the Wronskian to solve this non-homogeneous second order differential equation. Okay, the next problem that I want to do, okay, is a very well known physical problem, and that is of forced oscillations. Okay, so if you remember, we had the damped. So I'll just write in terms of so if you had m y double prime plus c times y prime plus k times y. Okay, so if you had this equal to 0, that would be a damped harmonic oscillator. Okay, second order differential equation with constant coefficients would correspond to a damped harmonic oscillator. Okay, now if this is equal to some function, I'll just call it c of t, okay, then you would call it a forced oscillator. Okay, so the right hand side is called the forcing term. Okay, so it is not equal to 0, so it is a non-homogeneous equation. Okay, and let us take the case when this forcing term has the form f0 cosine of omega t. Okay, and what I want to emphasize is that y double prime is equal to d square y by dt square. So t is the independent variable here, y prime equal to dy by dt, just to make connections with a forced harmonic oscillator. Okay, so my differential equation has this form m times y double prime plus c y prime plus ky equal to this. So this is the differential equation that I want to solve. I will call it equation 1. So what you have to do is to solve this differential equation. Okay, now so the first step is to solve the step 1 is to solve the homogeneous equation. Okay, so here you will get yh is equal to, so what we said is you get we wrote the general solution, okay, as you start with a trial solution. Okay, so you try your trial solution that you make has this form e to the lambda x. Okay, this is trial. Okay, and when you put this in the homogeneous equation, so you will get m lambda square plus c lambda plus k equal to 0. Okay, so that is the homogeneous equation. Okay, and this has the general, so the solution depends on the values of lambda. Okay, so you get 2 roots, so lambda is equal to negative c plus minus square root of c square minus 4 k m divided by 2. Okay, so if c square minus 4 k m is less than 0, then you get oscillatory solutions. If c square minus 4 k m is greater than 0, then you get only exponential solutions. If it is equal to 0, then you are right at the critical point where both the values of lambda become concurrent. Okay, so the general solution I can write as yh equal to c1 e to the lambda 1 x plus C2 e to the lambda 2x if lambda 1 not equal to lambda 2 and equal to C1 e to the lambda x plus C2x e to the lambda x if lambda 1 equal to lambda 2 equal to lambda. Okay, so that is what the general solution looks like. Okay. Now, what about the particular solution? Now, if you want to find a particular solution, you can just look at this. You can just look at this and immediately write the particular solution. So, since this is cosine, okay, what we said is that you should try a particular solution. So just you should try a particular solution that is a combination of sine and cosine. So, try yp of x is equal to a cos or yp of t rather a cos omega t plus b sin omega t, like this yp of t. Okay, so if you try this solution, should I use the same a and b? No, okay, I can use a and b. Okay, so now if you try this as yp, okay, yp is a particular solution of the same homogeneous of the same inhomogeneous equation. So if you substitute, so what you will get? So first thing you will see is that yp prime is equal to minus a omega sin omega t plus b omega cosine omega t. Yp double prime is equal to minus a omega square sin omega t minus b omega square cos omega t. So now if you substitute these in your differential equation, okay, so if you substitute yp prime and yp double prime, these are supposed to satisfy the differential equation 1. Okay. So when you substitute in this differential equation 1, okay, what you will get? You will get m times, you have m yp double prime. So you have minus m a omega square sin omega t minus m b omega square cosine omega t. Okay, so that is the first term, which was my double prime. Then you have cy prime and then ky. So what is cy prime? So when you take cy prime, okay, I will just collect all the sine and cosine terms separately. So c times y prime will give minus c a omega sin omega t. You should get cosine and here you should get sine. Okay, so this should be cosine, this should be sine, cosine and this should be sine. Okay. Now when you take now again I will just collect the sine terms and cosine terms separately. So this will be c b omega. So c times, so I will get plus c b omega sin omega t minus c a omega c b omega cosine omega t. So this is from c y prime. So when I take c y prime, the cosine omega t term looks like c b omega, okay, and the sin omega t term looks like minus c a omega sin omega t. Okay. So just to remind yourself, this came from y double prime, this came from c y prime, okay, then you have ky. Okay, so the third term was ky. So the ky term will have the form, so you have k times a cosine omega t. So I will write it here plus k times a cos omega t plus k times b sin omega t, and this whole thing should be equal to f0 cos omega t. Okay, this whole thing should be equal to f0 cosine omega t. So this is the differential equation, and what does this tell you? This tells you that this should be true for all times, Okay. So, therefore, the cosine terms should match on the right hand side, the sine terms should match on the right hand side. So, if you match the cosine terms, cosine omega t terms, then you get minus m a omega square plus c b omega plus k a equal to f 0. Okay. And if you match the sine omega t terms, then you get minus m b omega square minus c a omega plus k b equal to 0. Okay. And what this gives you, if you look at it carefully, this is, you want to determine a and b. So, these are two linear equations, and from these you can determine a and b. Okay. So, what will you get a as? So, I will just write it out explicitly, we will determine a and b. So, let us write this in the following form, we will write this as a times k minus m omega square plus b times c omega equal to f 0, and you have a times minus c omega plus b times k minus m omega square equal to 0. These are my two equations, and you can solve them and you can get the value of a and b. Okay. So, you will have a determinant in the denominator. Okay. And it is not very hard to see, I will just write the final answer. So, a will look like f 0 times k minus m omega square divided by k minus m omega square the whole square plus omega square c square. Okay. This is the determinant of this system, of the matrix that describes the system, and you will get b is equal to f 0 c omega divided by k minus, you will get the same term in the denominator. Okay. So, now you have the particular solution. So, I can write, I have the general solution and the particular solution, and I can write the overall solution. Okay. So, the yp of t is equal to f 0 times k minus m omega square divided by k minus m omega square whole square plus omega square c square into cosine of omega t plus f 0 c omega k minus m omega square the whole square plus omega square c square into sine of omega t. So, this is my yp, and I can finally write my general solution, which was y is equal to yh plus yp. Okay. And yh, you remember, if the roots were distinct, then it was c1 e to the lambda 1 x plus c2 e to the c1 e to the lambda 1 t plus c2 e to the lambda 2 t. Okay. So, again this should be t's here, not x. Now, this should be t. So, the variable that is used should be t. Okay. So, yh had these two possibilities, if lambda 1 is not equal to lambda 2, and if lambda 1 equal to lambda 2, then the second, then each case you have lambda. So, e to the lambda t, and the other independent solution is t e to the lambda t. This should be t e to the lambda t. Okay. So, we have managed to solve this equation of a forced oscillation. Okay. And we did this using a trial solution. Okay. And actually you can analyze the solutions. Okay. And you can show what is known as the resonance condition. Okay. When omega square, when this term goes to 0, okay, then you will find that the amplitude becomes very large. Okay. So, that is the condition of resonance, which you can show in this case. Okay. So, I will leave that as an exercise to you to actually try to look at various cases of this solution. Okay. But with this we will conclude the discussion on second order homogeneous and non-homogeneous equations. Okay. In the next week, what I will do is try to find a general method of solving the homogeneous differential equation. So far the homogeneous differential equation we have solved for the cases when you know one root, then when you know one basis solution, you can solve for the second basis solution by variation of parameters. Okay. But what if you do not know any root? How do you go about trying to generally solve a homogeneous second order linear differential equation? And in doing this we will come up with the so the general method that we will use is called the power series method. So the next 2 weeks we will be looking at the power series method and its applications. Thank you.